Okay, so today we are talking about discrete models, and in particular, we're going to talk about recurrence relations. So first off, discrete models essentially come into play anytime that you have some sort of quantity that changes over time, but it changes in such a way that the time scale is sort of large. So what I mean by that is rather than something changing continuously, you can either approximate it by something that changes every so often, so at some fixed time interval like a day or a week or a year, or it actually changes at that time scale. So it either changes approximately at that time scale or actually at that time scale. And so to give you sort of an example of a difference between continuous versus discrete time changes. So the human population, if you think about everyone in the world, that changes more like continuously, just because with this many people in the world that we're living in and how quickly people reproduce and die, things are almost constantly changing. So we would model that continuously just because the population is just going to change every second or even quicker. Whereas if you're talking about maybe the population of trees in a forest, that's not going to change quite as fast. And so you could approximate the change in number of trees discretely, so maybe just at the end of every year you look at how many trees there are in the forest, or even at the end of every 50 years or something like that. So that's an example to give you a better sense of what I mean by continuous versus discrete models. All right, so assuming then that we've got something that we can model discretely, we want to look at the change in that quantity, again over time, and because we're doing it discretely, we're going to look at the change in the quantity at the end of some time step. So again, that time step can be an hour, or a day, or a week, or a month, or a year, or any sort of fixed unit. And we can represent this typically, assuming that the way that something changes is constant, we can represent this as a recurrence relation. And so what we've got right here at the top of the page is the general form of a recurrence relation. And I apologize that the way my handwriting looks with my tablet is a little bizarre. It looks kind of like a robot writing, which I don't even know if that makes sense, but anyway, hopefully it'll be legible enough for you. So the general recurrence relation is defined to be x of n. So x is the quantity that we're talking about, and this n denotes that it's the amount of that quantity after n time steps. So the amount of the quantity after n time steps is going to be some function of the amounts of that quantity at previous time steps. And it may not explicitly be a function of all of its previous quantities, but just some number of the previous quantities, potentially all the way back to its initial quantity at time 0. Okay, so sometimes people see recurrence relations written where this n is a subscript, but we're going to use it as more of like this functional notation, so x of n versus x sub n, and that's just a choice that we're making. There are pros and cons to both notations, but we'll just go with it this way, and then some references that you look at may use the subscript notation, and that's just it's about 50-50 back and forth as to which one is used. Okay, so let's go ahead and look at this example. So here's a recurrence relation. That's x of n equals x of n minus 1 plus x of n minus 2. And one thing that I didn't mention before, which I guess I'll go ahead and add up here, is that your recurrence relation is going to have some number of initial conditions, which from here on out I might abbreviate as ICs. And that's just because if this is a function of some previous number of states, well, we have to know what the values are at some number of previous states to begin to even compute anything. So usually you'll need the same number of initial conditions as previous states referenced in the definition of the recurrence relation. So for instance, here where we've got x of n equals x of n minus 1 plus x of n minus 2, we have two initial conditions, one for x of 0 and one for x of 1. So we have the initial amount of the quantity and then the initial amount after one time step. So because we have these two, we can presumably calculate the amount of the quantity at n equals 2, right? Since we've got 0 and 1, and 2 will be defined in terms of those previous ones. So let's just go ahead and write out a few more terms in this relation. So x of 2, just following the formula, should be x of 2 minus 1 plus x of 2 minus 2. And so that will be the same thing as x of 1 plus x of 0. And for us, that's going to be 1 plus 0, which is 1. Continuing on, if I look at x of 3, that's going to be x of, let's see, 3 minus 1, this time just quickening it up a bit, is x of 2. And x of 3 minus 2 is x of 1. And so we know that x of 2 was 1, x of 1 was 1, so we're adding 1 plus 1, that's usually 2. Looking good. X of 4 is going to be x of 4 minus 1, which is x of 3. And x of 4 minus 2 is x of 2. X of 3 we saw was 2, x of 2 we saw was 1, so we're getting x of 4 equals 3. And we could continue on as long as we wanted until we get bored. One thing to notice is that every subsequent term in this recurrence relation is defined by the sum of the previous two terms, and that should sound familiar to you if it hasn't already started ringing some bells. So let's look at what we have so far. So if we think about this recurrence relation as defining terms in some sort of sequence, then the 0th term, which doesn't really mean anything, is 0. The first term is 1, second term is 1, third term is 2, fourth term is 3. The fifth term we could do in our head really quickly as the sum of these two is 5, so on and so forth. This is the very well-known Fibonacci sequence. I'm actually not sure if I've spelled Fibonacci correctly because I go back and forth as to whether it's a double N or double C, but I think it's a double C. So anyway, this gives us the Fibonacci sequence, and so now you know that this is how it's defined recursively as another term for that recurrence definition is also called recursively. Alright, so one of our goals in using recurrence relations is to find a closed form solution. And the idea behind this is, like I said, we could keep computing this recurrence relation forever and ever in this first example, right? But we have to do it one at a time using the recurrence relation, right? So we have to start at x of 2 and then go to x of 3 and then go to x of 4. So if we wanted the 127th term in the Fibonacci sequence, if we only have the recurrence relation, we have to compute a ton of terms, right? I guess 125 of them, because we have the first two, or really we only have the first one in the sequence itself, so I have 126 terms. And that's really tedious. Like, we can do it. There are even shortcuts to help us do it. So, we could program a computer or, an appropriate software package to do it for us quickly. But if we want to do it by hand quickly, the best way is to look for a closed form solution. And so closed form solution will basically allow you to, for any value of n, directly compute the nth, or the value of your quantity at the nth time step without having to do all of the intermediate time steps. So it's really useful if we can find a closed form solution. All right, so the example that we're looking at starts off with the recurrence relation x of n equals r times x of n minus 1. And here I want us to be sure that we know that r is a constant. And we also have the initial condition that x of 0 equals a, where a is also some constant. So again, I just want to point out that because we referenced one previous time step in our recurrence relation, we have one initial condition. So the way that we're going to find a closed form solution is by the iteration method. So what that means is I just start computing the recurrence relation like I did in the previous example with the Fibonacci sequence, but I'm trying to look for a pattern that I can then summarize to find a closed form. All right, so since I've got x of 0, I'm going to begin my computations with x of 1. So based on the formula, I know that x of 1 is going to be r times x of 0, and I know that x of 0 is a, so altogether I've got r times a. X of 2 should be r times x of 1, so that's going to be r times, well, x1 was r times a, so altogether we're getting r squared times a. X of 3 is going to be r times x of 2. So we're taking r times what x of 2 was, which is r squared a. So that's r cubed times a. And you might see the pattern now, but just in case you haven't, let's go ahead and do one more. So x of 4 is going to be r times x of 3, which is r times r cubed a. So that's r to the 4th a. And so maybe now you see, oh, every time we just increment the power of r by 1. And in fact, if you look from x1 to ra, x2 to r squared a, x3 to r cubed a, x4 to r to the 4th a, you might also notice that in fact, x of n is just r to the nth power times a. And so now this is our closed form solution, because if I have a specific value of n, I can go ahead and directly plug that value in here and have my overall amount of the quantity x at time n without having to do all of the previous steps. So a couple quick notes about this specific example. First of all, you might see the terminology geometric sequence when referring to the sequence of terms that arise from, or that arises from, this particular recurrence relation. And it's a geometric sequence with ratio r. And basically that just means that each term in the sequence is the previous term times that ratio r. Right? So we started with a, then we went to RA, then r squared a, so on and so forth. So anytime that from one term to the next you're just multiplying by the same constant value, that's called a geometric sequence with ratio r. So that's just good to know. Also, this particular form of recurrence relation and its corresponding closed form solution are also called exponential, just because we're taking that constant r, raising it to some exponent, and applying it to the initial value. So both of those are used to describe this example, which is actually a very general example, right? So we're saying that some quantity always changes by a constant multiple of its previous state. So whenever we have something that behaves like that, we know its closed form will follow this form right here. Oh no, I don't know how to avoid that from happening. Okay, so our second example, we're going to use the iteration method again. And this time it looks very similar to what we had before. We've got x of n is some constant multiple of its previous state, but then we're adding some other constant amount to it. So here r and k are both constants. The initial condition x of 0 is a, which is also a constant. At some point I'll stop writing that and just kind of say it, but just so we know. So presumably this is going to have a slightly different closed form solution just because in addition to this exponential piece, we've got some constant that's added every single time. And it is the same constant added every single time. Sometimes the constants, like, you know, I could have a k sub n here, right, where each time the constant amount that's added is a little different, and so that depends on which time step it is. But that's slightly more complicated, so for now we're just assuming that we're adding the same amount every time. Alright, so as before, we're just going to start writing out terms and see if we can determine a pattern. So x1 is r times x of 0 plus k. And we know that x of 0 is capital A again. So we have RA plus K. X of 2 is R times x of 1 plus K. So that's R times RA plus K plus K, right? Because I'm just subbing out x1 for RA plus K. So that gives me R squared A plus RK plus K. X of 3 is R times x of 2 plus K. So that's R times, subbing out x of 2 for its expanded expression. We've got R squared A plus RK plus K. Close that off and tack on that K. Gives us R cubed A plus R squared K plus RK plus K. And let's do one more, and then we'll try to generalize this. So x of 4 is R times x of 3 plus K. So that should be R times the previous expression we got. All plus K. And so that is R to the 4th A plus R cubed K. Now that I'm rushing, my handwriting looks worse. Plus R squared K plus RK plus K. Okay, so let's look back at this and see if we notice anything. So for n equals 1, we had RA plus K. For n equals 2, we had R squared A plus RK plus K. Then we had R cubed A plus R squared K plus RK plus K. And then R to the 4th A plus R cubed K plus R squared K plus RK plus K. Alright, so they're kind of two qualitative pieces to these expressions, right? There's stuff involving A and stuff involving K. And so if I generalize this, I notice that the stuff that involves A is R to the power n times A, right? So r to the 1 times a, r to the 2 times a, r to the 3 times a, r to the 4 times a. And then the second piece involving k's, well, we start off with just k, and then we have rk plus k, and then r squared k plus rk plus k, so on and so forth. So each time we're adding a new term that has a k and then a higher power on r times that k. So what I'm going to do is write this in summation notation, but first I'm going to factor out a k since it was involved in every single piece of the second portion of this expression. So I factor out the k, and then notice that I've got powers of r, and the highest power of r that I have is essentially n minus 1, right? So that's going to be the upper index on my summation. And then the lowest power of r is, well, 1, right, which is r to the 0. So my exponents on r start at 0 and go all the way up to n minus 1. So now altogether, I've got x of n equals r to the n times a plus k times the sum of I equals 1 to n minus 1 r to the I. So the thing that's important to note here is that we're not actually done with a closed form solution. This is great for the closed form solution because we can just plug in n and be done. But notice that here, when we plug in our value of n, we still have to add up a bunch of numbers for this r to the I summation. And that's still tedious, not quite as much as doing all of the terms up until n, but it's still more tedious than we like. So one thing that we're going to make use of is this thing right here. So this is a geometric series, geometric for the same reason that we talked about with the geometric sequence previously. So in a series, you've got terms of a sequence that are all added up, right? So whenever we have this summation, that indicates some sort of series. And in this case, we're adding up terms of a geometric sequence. So that's why this is called the geometric series, because each term in the sequence is just, you know, the ratio r times the previous number in the sequence, and then we take all of those numbers and add them up. So what's useful to note is that as long as r is not equal to 1, then that series turns out to be 1 minus r to the n all over 1 minus r. And it is an n here, even though we're going from 0 to n minus 1. So that's important to note. And then if r is equal to 1, well, let's think about this. So if r is equal to 1, then no matter what the exponent is on it, the term in the sequence is 1. And then we're adding up from 0 to n minus 1 ones. So we're adding up n ones. So that should just end up being n altogether. It might, if that's confusing, it might help to actually write that out. But so we can summarize then this closed form solution as being x of n equals r to the n a plus k times 1 minus r to the n over 1 minus r, assuming that r is not 1, and it would be r to the n times a plus k times n if r is equal to 1. So those are our two possibilities for the closed form solution. Sorry that I had to squeeze that in, but hopefully you can make sense of it. Okay, so let's look at a quick application of what we've just talked about. And so in this example, we're modeling a population. I started off, you know, this lesson talking about discrete versus continuous, and the example I gave you was in populations, and so that's just a really common application for discrete models, and for many models actually. Okay, so this time we're assuming that we've got a country. It currently has 100 million people, and the population growth rate, which is birth rate minus death rate, is 1% per year. It also receives 100,000 immigrants per year, which are quickly assimilated and reproduce at the same rate as the native population. So we want to find the population of this country 10 years from now. And we also assume that all of the immigrants arrive in a single batch at the end of the year. Okay, so let's think about what this means in terms of our recurrence relation. So if there are currently 100 million people, that sounds like an initial value. So that's like an x of 0. And 100 million is 100, followed by 6 zeros. Let's see what else. So it seems like we've got a population growth rate, and because it's a rate, we know that some change corresponding to the amount of the population at a certain time, right? So the rate is like people per year or something like that. I didn't explain that very well, but I think you guys get what I'm saying, right? So if I've got, let's just say I start with 100 people and it changes by 1% per year, well, that's 1% of those 100 people, which means we would increase by 1 for that year, but then the next year it would be 1% of the 101, right? So that 1% is an increase based on whatever the starting population is. And that's probably just the way I should have said it to begin with. Also, it's important to note that that's just the growth part of the change in population, but we also will maintain this initial population and then just add to it, since this is a positive growth, right? We're already taking birth and death into account. So because this is a net positive change, we're going to start with this amount and then add to it. And so the reason that I'm making a big deal out of that is because it's really tempting to put your R as 0.01 to represent this 1%. But really R here is 1.01, because if we're applying, let's see, let me scroll up really quick. I still don't know why that happens. Okay. If we're applying R to the previous population, then we want to say, all right, our new population is going to be what it was, plus some growth, plus maybe something else. And so in order to get what it was, we have to have this 1 here. So you can think of this as x of n equals x of n minus 1, right? So that's our starting population plus its growth. And then maybe plus something else, which we'll see in a minute. And so we could factor out the x of n minus 1 here and get r as 1.01, right? So that comes from here. Okay, so I've mentioned that in addition to that growth rate, we might also add something, and you all know that that's coming from the immigration. So we know that in addition to just the birth and death rates, we're adding to our population by a value of k equals 100,000. So I'll go ahead and denote that just in terms of the original parameters of the problem setup. Okay, so we don't want to use the iteration method here because we already did it for the general case up above, right? For something that has x, r, and a k not equal to 0, we can use one of these two closed forms without having to redo the iteration method, right? That's what's nice about the closed form solution. So what we first want to do is determine whether we're in the case where r is not 1 or where r is 1. R is very slightly above 1, so we're going to use this first form of the solution. So that means x of n is going to be r to the n, so in this case that's 1.01 to the nth power, times that initial value of 100 million plus k, which is 100,000, times 1 minus r, which is 1.01, whoops. Let's see, I think I can erase this. I can. Okay, so 1 minus r, which is 1.01 to the n, all over 1 minus r. Notice that the numerator and the denominator are both negative, so this will net out to positive, which is good because we want our population only to increase, right? It's got a positive growth rate, and then we're also getting some immigration, so altogether our population should increase in both directions. So that's a good little reality check for you. And then we were asked specifically for the population after 10 years, so we're going to plug in n equals 10. So 1.01 to the 10th times the 100 million plus 100,000 times 1 minus 1.01 to the 10th all over 1 minus 1.01. And you can confirm for yourselves that depending on how many decimal places you keep when you do this computation and this computation, the population is going to be approximately 111,508,434 people in that country at the end of 10 years. And again, this is approximate because of the number of decimal places that you keep. So if you get something that's a little bit different, it's probably not a big deal. If you get something vastly different, then we should talk, because I might have made a mistake, or you might have made a mistake. Alright, so I think I'm going to put this next piece in a second video just to keep the time down on these things. So I will see you guys in just a minute.